Good day, Algebra 2. This is Mr. Morales, and we're going to be on Day 23 notes talking about what are called reciprocal parent functions. Now, you probably won't remember or refer to this typically as the reciprocal parent function. What it basically is another type of graph. Up until now, in Algebra 1 and Algebra 2, every graph we've dealt with has been basically, if we wrote it out, it would be a numerator. We haven't graphed anything with fractions. And what I mean by that is we haven't had any kind of equations where the stuff we're plugging in was in the denominator or in a fraction. So today we're going to begin graphing what are called reciprocal parent functions. You can kind of think of it as basically fraction types of graphs. Now, so here's what I mean. A lot of the work will be happening in the denominator of these fractions, at least for this first set of notes. Now, when you graph this particular function, 1 divided by x, you get a very unique graph. The type of graph you're going to get is called a hyperbola. And it has a very distinct shape. Now, what makes this graph different is that it has a lot of restrictions. For example, its domain. The domain can be every number except for one particular number. The one number it cannot ever be is 0. And that's because you can't divide by 0. Dividing by 0 isn't something that's possible to do. So what happens is you start graphing 1 divided by x. You start putting 1 divided by -10, by -8, 7, 6. And then what happens is you get this sharp turn going downwards. And what's happening is that this graph is getting really close to the y-axis, to x equals 0. But because it can't ever equal 0, it'll never touch. So what we have is what we call an asymptote. Basically, it's like an invisible border. And the y-axis is an asymptote. It's a border that our graph can never touch. So our graph can never be anything. It can be any negative number we want, and we can get as small as we want, but we can't ever get to 0. On the other hand, once we pass 0, and you go to any amount greater than 0, any number at all, the graph continues on the other side of the x-axis, on the y-axis and x-axis, and continues on its merry way. However, if you notice that the graph on both the left and the right-hand side never seems to touch either axis. And that's because it will never, I keep trying to draw and I keep messing it up, there we go, has another asymptote. So what happens is you get this nice little shaped graph. It's this really interesting curve that kind of gets really close, shoots down, gets infinitely close to 0, but never touches. Once you skip 0, it continues back again from left to right, and now it increases infinitely, because the bigger you divide by, the smaller your number gets, and it gets infinitely close to the x-axis. So what we have are two situations here. We have you can have any y value you want for an answer, except you can't ever get a y equals 0, because you're always going to have a number in there. So as long as zeros are never involved, your graph does go infinitely left, right, up, and down. We have the asymptotes, that's how you say this word here. Basically, those are imaginary borders that keep your graph in check. That's what those yellow dashes that I drew were. And your asymptotes are at x equals 0, which is your y-axis, and y equals 0, which is your x-axis. Both of those kind of keep our shape in check. Now, just like many other graphs this year, there is a way that you can shift this graph around. You can stretch it, you can move it left, right, up, and down, and it behaves in the same way that we've actually managed before. So the equation, the standard form for reciprocal function, so the way you would write an equation if you want to move it around is as follows. You're going to have some number in the numerator, and you're going to have x minus h plus k. This format should look familiar. H is the horizontal or sideways movement. And just like we had with other graphs, this one is the opposite. For example, if you have a positive number you're adding in the denominator, that's going to move your graph to the left. If you have a negative number in your denominator, or if you're subtracting a number, that's going to shift your graph to the right. So it seems opposite. Although adding numbers, we think going to the right, it means it's going to go left. And when you're subtracting a number, it's going to do the opposite, go to the right. If you have a number outside of the fraction that's being added or subtracted, this is going to affect your vertical shift, your up and down movement. And this one is exactly what it looks like. If you have a positive number, you're going to shift up. If you have a negative number, you're going to shift down. Also, the numerator. If a is negative, the function then is going to be reflected over the x-axis. So we're going to mirror image going up and down across the x-axis. And then, just like before with other graphs, if a is bigger than 1, then what you have is a vertical stretch. There we go. And if a is any number, any decimal fraction between 0 and 1, positive or negative, then you have a compression. It's going to be more shrunk down or squeezed. Now let's practice some of these things. Oh, and your vertical asymptote. Now this is really the key to all the questions you can be asked. So where are your boundaries? Where are those yellow dashed lines? Because if you shift your graph left, right, up, and down, those yellow boundaries are going to change. So an easy way to find your boundaries, which is going to be a good first step, is to find your vertical asymptote. That's going to be a line that bounds your graph going up and down. And that's going to be x equal to whatever your h value is. I want to say it as negative h, the opposite of whatever h looks like when you plug it into the function. You'll see what I mean in a few moments. Your y asymptote, however, is going to be whatever your k value is, whatever you're adding or subtracting outside of your reciprocal function equation right there. All right, so let's practice this. They give us some parameters. So what I'm going to do first is I'm going to go ahead and write down the standard form function. So that's f of x, lock this down, f of x equals a over x minus h plus k. Now let's see what the specifications are. We want the reciprocal parent function, that's what I have here. We want to reflect it across the x-axis. That's one of the things we have to have. Then translate it 4 units to the right and 3 units down. Write an equation to represent the new function and identify the asymptotes. So I'll begin with f of x. First piece, it tells me that's reflected across the x-axis. It makes no mention of any kind of compression or stretch, so I would assume I have a positive one to begin with. Since I want it to reflect over the x-axis, it now becomes a negative one. Reflections mean you have a negative number on top, period. Then I want to translate it 4 units to the right. So down here in parentheses, x. If I want to go to the right, then I'm going to have to go minus 4, because remember, it looks like the opposite. Subtraction in the denominator for this means you're moving to the right. Addition means you're moving to the left. So I want to go 4 units right, and then now I'm going to have a vertical or up and down movement. In this case, I'm going to go 3 units down. So there's my equation. I'm also asked to identify the asymptotes. So, my asymptotes. To get my vertical asymptote, that's going to be x equals, and the opposite of whatever I'm adding or subtracting. Since I'm subtracting 4 here, I write it at positive 4. And then my horizontal asymptote, oops, let me write it up better. My horizontal asymptote, HA, begins with y equals, and that's whatever I am adding or subtracting outside of the fraction. And that would be minus 3. Those 2 lines will become more important on the back side when we start graphing these. They set up the boundaries of your graph. Now let's go ahead and move on. Number 2, let's try this again. So let's write our standard form formula, f of x equals a over, and I'll just put in parentheses, x. I guess you could say plus or minus h, right? Plus or minus k, because we don't know if we're going up, down, left, or right just yet. All right, so now let's go ahead and look at our criteria. The reciprocal parent function is vertically stretched by a factor of 2. Okay. Then translated 7 units up and 1 unit left. So I'm going to have at least 3 different numbers plugged into this equation. Write an equation to represent the new function and also identify the asymptotes. All right, so I know it's going to be stretched by a factor of 2. So I'm going to go ahead and just throw a 2 on top because everything on top has to do with stretching or compressing. as well as reflecting if that was an issue. It doesn't mention reflecting, so my number just stays the 2 that they gave me. Now, x on the bottom. I'm going to go 1 unit to the left. That means I'm going to have a +1 on the bottom. Careful, they gave me that up and down first, and then they gave me the left and right. So make sure you read carefully. I am then going to translate this graph 7 units up. So now, to get my vertical asymptote, that's going to be x equals the opposite of whatever I see in here, which is going to be a -1 and -1 in this case. And then my horizontal asymptote is whatever I'm adding or subtracting, and that's going to be 7. All right, one more example of writing the equations. I'll just write the equations by themselves. So I began with the standard form, parent equation. We'll say plus minus. All right, so now let's see what standards or parameters they set for me. A reciprocal function has a vertical asymptote located at x equals 2. So now they're giving me a little backwards stuff. A vertical asymptote at x equals -2. That will be helpful. And a horizontal asymptote located at y equals 5. So horizontal asymptote at y equals 5. So work backwards. I know that the horizontal asymptote is what's being added or subtracted to the end of my equation. A +5 means I'm adding 5, I'm moving it 5 units up. The vertical asymptote is going to be the opposite of whatever I have in my equation. So if it's a -2 here, that's going to be a +2 in my equation. And then it also tells me to say what else. It doesn't tell me anything about shrinking or compressing or reflecting, so I'm just going to throw a 1 for A. So there is my equation, and there are my asymptotes already given to me. So how do we use all this information? Well, let's go ahead and look at the back now. So typically, our graph is going to always look something pretty much like this. And we're in charge of finding out where the different asymptotes or borders are. Depending on where they shift, it tells us on how our graph's going to look. So for number 4, what we do know is that we're going to have a domain, and the domain's always the same. X is basically all real numbers, except x can never equal 0. Now we also have a vertical asymptote. Now in this case, we're not adding anything to x. So our vertical asymptote is that x equals 0. So I'll go everywhere that x is equal to 0 and make like a dashed line. This acts as a boundary. X equals 0 is the same thing as your y-intercept. So here's every place that x equals 0. There's one of my boundaries. I'm going to make this a little more obvious to stand out. Now, the range. The range is determined by what's either being added or subtracted. The only problem is it can't be the number that's being added or subtracted. So my range is every single number for y except that -2 that I have included at the end. So that means I have a border or an asymptote at y equals -2. So I'll go to the y-axis, I'll go to -2, and I'll make a line that goes through every point where y value is -2. Now I have no kind of reflection or anything going on. I can go ahead and make my graph. I'm going to just, for this assignment, I'm going to go ahead and just give you the rough points. We'll focus more on getting the exact points later. I want to get just the rough idea of what the graph should look like. And it looks like our regular graph, only slightly shifted. In this case, shifted down 2 squares, 2 units. My graph should be a lot more accurate than that. And really, I would recommend maybe even using table values to get a few good anchor points. Usually at 1, 1, and -1, you have something going on there, but we'll get into that more later on as we do more of these. Right now, just focus on the graph. So number 5 continues the same exact way. The domain is going to be whatever makes the bottom equal to 0 by denominator. So x can be all numbers except for a -3. Because if I put a -3 for x, then I'll get a 0, and you can't have 0. So I'm already going to have an invisible asymptote at x equals -3. My range is going to be anything that I'm adding or subtracting at the very end. And I am not adding or subtracting anything, so that means my range is going to be, y can be anything except for 0. So I'll have a horizontal asymptote at y equals 0. So I'm going to go ahead and make my asymptotes. Make them a little bigger so they stand out a little more. So let's go first to x equals negative 3. X equals negative 1, 2, 3, and I'll make my asymptote right there and move this back down a little bit. Don't know why it jumped. Alright, so negative 3. Alright, those were my asymptotes. Let me erase these points I made. And then I'm going to have another asymptote at y equals 0. Y equals 0 basically means your x-axis. So it'll look like this. I have no talk of reflection or anything happening in my graph. So I'll go ahead and just make a rough sketch of what my graph's going to look like. And so all I have is a graph that comes in from the left, shoots down this asymptote, and then it will start back from the left and continue on to the right. Arrow tips on both ends because it does go in both those directions infinitely. So we have a graph that's been shifted 3 units basically to the left with no up and down change. So now let's go ahead and look at number 6. And we can already make some predictions. We know it's going to be reflected over the x-axis because I have a negative. It's going to be stretched out more because of that 4. On the bottom, it's not going to move left or right. So since it doesn't move left or right, I'm not adding anything. X can be anything but 0, which means that my asymptote, vertical asymptote, is at x equals 0. My range is going to be anything but positive 1. So then my horizontal asymptote is at positive 1. So let's see what that means. So at x equals 0, that's basically your y-axis. I'm going to go ahead and have my boundary, my asymptote. At y equals positive 1, I have another asymptote, so I'll draw that here. Typically, the graphs come in like this and then come back like that. Since I have a negative 4, it's going to be stretched out and flipped. So what I'm going to get is a graph that swoops up from the left and then shoots back to the right from the bottom to the negative 0, like that. And that's what my graph will look like. And it's going to be more stretched out, but we're just kind of just giving us, like I said, focusing on the general characteristics right now. We'll get the exact numbers in our future assignments coming up. Number 7, now we have quite a few transformations happening here. We have a positive 3, so my graph should still generally go like this, which is fine. It's going to be more stretched out though because 3 is a number bigger than 1. Minus 2 means it's going to be shifted 2 units to the left. So x can be anything but a positive 2. Because 2 minus 2 would be 0. You can't have a 0. So if at x equals positive 2, I'm going to have one of my borders. Positive 1, positive 2, I'll make my border. Notice that I say x equals 2 because this imaginary border, asymptote, goes through positive 2 on the x-axis. That's what it means. So there's one of my imaginary borders right there. Next, the y value. Well, y can be anything but what's attached at the very end. In this case, it can't be a negative 2 because I have minus 2 attached. So at y equals negative 2, I have another asymptote. So I go make a line that goes through the y-axis and negative 2. Now, I don't have any kind of reflection going on. I can go ahead and create my general graph, which will look pretty much like that. Should be maybe a little more flattened or a little more wider, more of a curve maybe. But for right now, I just want to get the general shape. And that's what it would look like. Now, let's go ahead and go on to number 8. For number 8, same type of thing again. So what I have is a positive 2 on top, so that won't affect at least it won't reflect my graph. I'll make it slightly wider. Plus 4. So my domain can be anything but a negative 4, because negative 4 plus 4 would give me a 0, and you can't have a 0 in the denominator. So I have a vertical asymptote at x equals negative 4. Negative 1, 2, 3, 4. I'll make a asymptote line going down. Now let's figure out the horizontal asymptote, which is based off the range. The range can be anything but what's attached at the end. And in this case, that'd be a negative 7. So at y equals negative 7, 1, 2, 3, 4, 5, 6, 7. I'll have another asymptote. I don't have any kind of notation that tells me it's going to be reflected, so it should follow the same pattern as the other one. So it's going to, a little piece of it will shoot down like that. And then we have all this space up here that it comes back from. All right, and our final example, number 9. This one's got quite a few transformations. We have a reflection over the x-axis with the -1. Our domain is limited by the opposite of that. So basically, x can be anything but a positive 5, because 5 minus 5 would give us 0. So we have a vertical asymptote at x equals 5. 1, 2, 3, 4, 5. I'll make my vertical asymptote right now. Vertical meaning up and down. A horizontal asymptote is where my range cannot be equal to, and that would be at positive 3. So at y equals positive 3, I have another asymptote. Now I can go ahead and just graph these two. Remember, I have a -1, which means it's going to be reflected. So instead of coming in from the left and going down, it's actually going to shoot up from the left and go up, and then come back down, shoot from the negative world and go back to the right like that. All right, so those are the basic characteristics of how to graph hyperbolas given the standard reciprocal parent function. All right, we'll have an assignment that goes with this given to you either today or tomorrow. All right, if you have any further questions, please feel free to ask me. Thank you and best of luck, guys.